Okay, so in the previous lecture we were discussing about a lattice. In this lecture we will introduce the notion of a torus. The notion of a torus. Now students who already have studied concepts of algebraic topology, they already know what a torus is and how do we geometrically construct out a torus, and what are the various topological properties of it, and that is the direct introduction we usually consider. In this case we are not gonna immediately dive into the geometric overview of what a torus is, but rather we'll introduce this as a quotient group in terms of a lattice in an n-dimensional Euclidean plane, and then study the geometric behavior which is which is trivially induced in it by considering it to be a quotient group, because we already know what are the geometric properties of a lattice. Okay, so yeah, so let me just write the goal. So we are intended to study, as I said, we are intended to study the quotient group Rn model, the quotient group where L is a lattice. I don't need it to be an n-dimensional lattice readily, but still we will discuss that. It can be any dimensional lattice with dimension less than n as well. So where L is a lattice in Rn, and then study the geometric behavior of it. Okay, so this is our goal for this lecture. So the first lemma which we start with today is the following. We first consider a set S, which is the collection of all elements in the complex plane such that the modulus of each of those complex numbers is 1. Okay, now so the first thing to observe, which I can immediately include inside the lemma itself, that S forms a multiplicative group. S forms a multiplicative group. Okay, this is the first thing to observe, and we call this the circle group, called the circle group, or it's also specifically also called the unit circle group. Okay. The quotient group R mod Z is isomorphic to S. Clear? Now before diving into the proof of this lemma, which is indeed quite simple, let us first get into a few notions of what these S things are typically. So yeah, so let us quickly talk about this. So primarily, okay, first thing first, let us first observe what's happening in this statement of the lemma. Okay, observe that R can be simply considered as R1 and Z. So this is only a one copy of a Z, so I can think of it as a one dimensional lattice, right? So this is just a one dimensional lattice inside R1. Okay, and R1 modulo L1 as a quotient group, this is isomorphic to one copy of S. Okay, this thing is something to be kept in mind because we are going to generalize this fact. Okay, now typically Bn, this gives us the n dimensional, ball. Now these are some some notations we often use in case of studying algebraic topology. So Bn is basically an n dimensional ball. Okay, n dimensional ball in the case that if we are talking about in R2, then any disk any disk, let me say any closed disk will come under the two dimensional ball. Okay. But Sn, in the same case, it is the n minus 1 dimensional circle, you might say. Okay. So typically I don't want to introduce this as a dimension. I can think of Sn as in this way. So suppose, okay, so let us consider R2. Okay, let us consider R2, and let us consider a solid sphere. Okay, I am considering a solid sphere. So yeah, this will be good to go. Okay, so this is a solid sphere. A solid sphere. Now you can easily observe that this solid sphere is nothing but a three-dimensional ball. Is a three-dimensional ball. I extract out its boundary. Okay, del B3 is what we mean by the boundary of the ball. Okay. So suppose by definition, suppose I say this ball has radius say 3. Suppose this is the closed ball centered at origin of radius 3. So this will be the collection of all elements x in R3 such that their norms are less than or equals to 3. And about the boundary of B3, I mean the collection of those points which are exactly on the surface. So I can think of it as the collection of those vectors which have their distance from origin exactly equal to 3. Then this boundary, if you carefully observe, then this is just the hollow sphere. This is just the hollow sphere. This boundary, it will consist of only the surface, okay, the surface of the sphere, if you carefully observe. And the surface of the sphere, if you zoom inside the surface of the sphere, you will see that it's a sort of seems like a plane. Okay. What I mean to say is that suppose I choose, suppose this is a hollow sphere. Suppose this is a hollow sphere, and let us choose any small portion on the sphere. Any small portion on the sphere. Now, if I zoom inside here, it seems locally, because we are talking about a small portion on the sphere, it seems locally, it seems to be R2, right? It seems locally to be a plane. In fact, if you measure any coordinate, if you measure any coordinate over the surface, you will see that actually this is a two-dimensional object. It seems to be a two-dimensional object, not a three-dimensional object. But nevertheless, you can't fit it inside a 2D plane. It will always reside inside a 3D plane. But it's geometrical, or rather it's topological, from the topological viewpoint, it's nothing but a two-dimensional figure. Generalizing this fact, whenever we are in some n-dimensional Euclidean space and we consider an n-dimensional ball, if I talk about its boundary, we get n-1 dimensional sphere. So Sn is often referred to as the n-1 dimensional sphere. Okay. So in this case, when we are talking about S, so S can be considered as S1. So S can be considered as S1. So it should be, so basically, so this is typically your S by our notation, right? Actually, the circle, whenever we talk about a circle topologically, a circle is referred to as S2. Why is it referred to as S2? We are using the notation here simply S because we do not need the notion of n-dimensional ball as such, n-dimensional spheres as such, but it is being referred to as S2 because it actually is a one-dimensional object. And the reason is, if I consider R2 and I consider the unit disk, because in this case we are talking about the unit circle. So if I talk about the unit disk, so the unit disk is like this, right? It's centered at origin and it has radius 1, and we are talking about the closed disk, so it is some sort of this thing, right, clearly. But what I want to do is that I just want to extract out its boundary, so I'll just extract out its boundary. So if I extract out its boundary, I get this. And if you carefully observe, so I can say you make you understand that this, why is it one dimension in a following way, that if I just flatten it down, if I flatten it down, then it will become, so if I press it from above and from below, it will become a line, right, it will become a line. Or if I am able to puncture it down at some point, it will become a line. But nevertheless, you do not need to visualize it and in that way as well. If I choose any point on this circle, if I choose any point on this circle, a neighborhood of this circle, if you carefully consider locally, I am again talking about locally, you will see that it is nothing but an interval, and simply a one dimensional interval, if you observe. You are getting my point? You cannot construct a boundary which is of this form, because these places are absent. Clear? Okay, so this is the overview of what an n-dimensional ball and what an n-dimensional sphere looks like. So nevertheless, let's get back to the proof of the lemma. And the proof of the lemma is quite simple. If you have studied complex analysis, even very basic complex analysis, you know what is the what should I say, equation. Yeah, it will do. What is the equation of a unit circle in terms of a complex number? It will make it very clear. So the proof of the lemma is that we need to show that R mod Z is isomorphic to S. Okay, this is what we need to show. And so this is just a quick overview. If I go to the complex plane and I see the unit circle there, so this is the S inside the complex plane, and I choose any point out from here, then this point is nothing but e to the power 2 pi I x, where x is some real number. Okay. So provided we choose any real number, if I map it to e to the power 2 pi I x under some restrictions which we will be following soon, we'll get to this unit circle. We can shrink that down to the unit circle. And the reason is that e to the power 2 pi I x, this is nothing but cos 2 pi x plus I sine 2 pi x, and the modulus of this is 1. And if the modulus of this is 1, then it is precisely over this unit circle. Okay, clear? Okay. Now okay, now let's get back to what we were proving. So as I said, what we do is that we just consider a map. We consider a map f from R to S such that f maps f maps a real number to e to the power 2 pi I x. Okay, this is the function we'll need at most. Okay, and this map is clearly surjective. There's nothing complicated in there. The map is clearly surjective. The map is clearly surjective. Moreover, f of x plus y, if I choose, then this is nothing but e to the power 2 pi I of x plus y, but this is e to the power 2 pi I x times e to the power 2 pi I y, and we know that the circle group is a multiplicative group. The circle group is a multiplicative group. That's quite easily, it follows from the fact that if I choose the modulus of a product of two such elements from the unit circle, then it will just break into the modulus of two of those vectors, and each of these individual vectors will be 1, right. There is nothing complicated in seeing that. In fact, you can also talk about the inverse. It will also give you of modulus 1, okay. And you can also check that it's a multiplicative group by choosing the elements to be of the form 2 pi I x, e to the power 2 pi I x, whatever. So this is indeed a group homomorphism. What is the kernel of F? The kernel of F is the collection of all elements, the collection of all elements x in R such that e to the power 2 pi I x is equals to 1, right. 1 is the identity of S. So now if you can carefully observe that this happens, now this takes place if and only if x is a natural number. In fact, x is an integer. Because let us come back to this characterization where I said that what did I write it down? Okay, I think I removed it out. Okay, so as I said that e to the power 2 pi I x is nothing but cos 2 pi x plus I sine 2 pi x. Now if you carefully observe that whenever I choose x to be an integer, then cos 2 pi x will become 1 and sine 2 pi x will become 0. So eventually it is just 1, right. Therefore, so since this is at both sided implication, therefore the kernel of F is nothing but the collection of all integers. In fact, it's just z. Therefore, by the first isomorphism theorem, so I have shown it to be surjective, right. So then R mod Z is isomorphic to the image of R under F, but we know that F is a surjective map, so it is the whole of S, and that is the proof required, okay. Now this brings us to a certain definition of a torus, which we will see that it eventually coincides with the one we usually study, okay. So now we define the n dimensional torus. We define the n dimensional torus as Tn, and we define it just to be n copies of S, okay. We define it just to be n copies of S, okay. So let me just give a quick recall of why this definition actually works as a general definition of a torus. If you have studied the topological structure of a torus, then you will know that it considers a structure like this, and I have it like this. So this is what we will call by our definition as T2, because here are two copies of Z, if you quickly recall, because there was a circle, a unit circle which came up like this, and there was another circle which eventually came up like this, okay. So in fact we have two copies of a circle crossed with each other, and so we can in fact generalize this out to talk about the n dimensional torus, because if you carefully observe that I have this as an S, I have this as an S, and so T2 is nothing but S cross S, right. Because if I consider this, and if I consider the section which this blue circle follows, and I can construct the whole of T2, clear. Okay. So first thing first, we want to generalize the first lemma which we had, so, and we can just present it as a theorem. The theorem says that if L is a n dimensional lattice, if L is a L dimensional lattice in Rn, so it is observatory that we are talking about a n dimensional lattice inside an n dimension Euclidean plane. So the dimensions match in this case. So if L is a n dimensional lattice in Rn, then Rn mod L is isomorphic to Tn. Okay. Now the things which first things to observe is that L, since L is a n dimensional lattice, L is isomorphic to direct product of n copies of Z, n copies of Z. So this lemma can also be thought of in this way. It's Rn cross Zn isomorphic to Tn, I can refer to as Sn. So it's just a generalization of the lemma. Okay, it's just a generalization of the lemma. Okay. Now see, one thing to observe here is that Rn, it consists of n tuple of real numbers. If I choose each coordinate, each component of this tuple, and if I map it to a one dimensional unit circle and I do it for all the components, I have a complete map, a complete surjective map to the n dimensional unit circle, right. So that will be the exact procedure to prove this. There is nothing complicated in this case anymore. In fact, so what I do is that let E1, E2 till En be the basis of L, be the basis of L. Consider the map. So if I just consider the map from the basis, it's good to go, because these basis elements will span the whole of the set and it will in fact make it to be surjective. There is nothing complicated in talking about that anymore. So consider the map F from Rn to Tn by, so what are we doing? We are mapping any linear combination of these elements A1 till An, and what I said is that I will just take each coordinate of the vector we are talking about and I will map it to a one dimensional unit circle. So if I take the first coordinate, I will map it to the one dimensional unit circle in terms of e to the power 2 pi I A1. Then I will take the second component, second coordinate A2, and I will map it to another one dimensional unit circle A2, and I will continue this for all the n components, n coordinates, and I left with An. So I will map it to e to the power 2 pi I n, and we are good to go. Okay. Now see, this is just a component wise analysis to observe that since the first in the lemma we had a surjective map, it immediately follows on the same steps that this map is also surjective, right. In fact, the kernel of phi, if you follow, the kernel of phi actually it considers elements x from Rn such that whenever there each coordinate of that vector is mapped in this way, it must equal you can think of it to be it must equal the elements 1, right. So let me be not that mathematical, you can fill in the gaps on your own. See, if I want this to be mapped to the vector 1, then I need each of these components to equal 1, but if I need each of these components to equal 1, I actually have this equation 2 pi I Ai to be equals to 1, and this is the equation which we had followed from the first lemma, that this has a solution if and only if Ai is in integers. So in fact each of these components or rather each of these Ais must be integers, and if each of these Ais are integers, then this map is nothing but Z finite copies of, or rather, so if each of these Ais are integers, then the collection using this if I have A1 E1 and so on till An En, if I consider this collection now where each of these Ais are coming from integers, then this just constitutes the lattice. Or if from the first lecture it is quite evident that if I just consider the map which takes each of the components of this vector to Z, then I will get a group isomorphism, and in fact this is nothing but Z cross Z n times, right. So in fact this immediately gives us the proof of this, because what we observe out from here is that, so that the kernel of F is Z direct product of a finite copies of Z, and there are only n copies of Z. So we have n copies, and this is nothing but this is isomorphic to the n dimensional lattice L, therefore Rn modulo L is isomorphic to Tn, or you can also consider it to be just Sn, right. But now here's a important thing which we would require to observe is that what if we restrict this map F to the fundamental domain. Okay. Now we will see the how the topological notion and this algebraic notions will eventually coincide. Now suppose we restrict this map F from the previous proof to the fundamental domain of the lattice. Okay. Now if you quickly recall that the fundamental domain of the lattice, it's basically consisting of the points of the lattice with their coefficients, or rather the fundamental domain, it typically considers the section, the section from the n dimensional Euclidean space where each of the vectors have their coordinates in the interval closed 0 open 1, if you recall from the previous lecture the definition of a fundamental domain. And if I restrict it to that case, then you can easily observe that the kernel of F will be immediately 0, because for the kernel of F only collects those coordinates which are integers. If I restrict an integer to the interval closed 0 open 1, within that interval, then the only possibility for that integer is to be just become 0. But if it is 0, then I will have an isomorphism from, so I am restricting it to the fundamental. So I have typically T upon kernel of F isomorphic to Tn. This is what we were eventually having, but we are seeing that the kernel of F will eventually become 0. So this implies T is isomorphic to Tn. So this means that the n dimensional fundamental domain, is isomorphic to the n dimensional torus, Now if you quickly recall that what was the geometrical figure represented by a fundamental domain, so it was just a rectangle, if you quickly recall, or you can also think of it as a square, right? So this whole thing was what we call the fundamental domain, and we are seeing that this fundamental domain is isomorphic, so it's isomorphic to Tn, which is the n dimensional torus. Now if you guys have studied algebraic topology, you will get to know that what we are going to do. So suppose in R2, let us consider in R2, I consider the fundamental domain. So this is my fundamental domain, say this is T, and then we will follow the usual procedure. Okay, so this is a solid domain, so this is solid. So now what I do is that I need to construct a torus out of it, so I will just identify each of its edges. So I will just transform it completely to a torus, and for that what I will do, I will just identify these two edges in the same orientation, and I will just identify the vertical edges, the horizontal edges also in the same orientation. So if I first identify the let me just use a different color for the vertical edges, it will be good to observable then. So if I do the vertical edges first, then I will get a cylinder. If you carefully observe, I will get a cylinder, because what we are doing is typically we are just rolling out, we are just rolling the square, okay, to meet to make both the edges meet. So if I get out a cylinder, I still have the upper edges, and then I want them to meet. So for them to meet, first thing I will do what is that I will just lay it down. I'll just lay it down, and I have these like this. Think of it like this, and I'll just want them to meet in this way. So in a similar way, so at some point I'll get a figure like this. Okay, so I'll get a figure like this, It's often difficult to draw it out. Yeah, I'll get a figure like this. Some sort of like this, right? And okay, sorry, this is good to go. I'm getting it from here, and then I can just make both these edges meet along the same direction, and I'll get the complete torus, where you can observe that this identified edge, it constitutes one circle. Let me draw it in a bigger way. Okay, so now you can observe that one of the identified edges, this vertical, these horizontal edges, it constitutes one of the circles here, and the other edge which we have, the horizontal edge, it will constitute the vertical edge, sorry, it will constitute this circle. Clear? Okay, so and this is exactly the topological construction of a torus. This is exactly the topological construction of a torus, and now we can see that this topological construction is kind of well defined, because we know that this rectangular plane, this rectangular section from an n dimensional plane, or rather let us say from R2, this rectangular section from R2, it's just isomorphic to the two dimensional torus, right? And hence this topological construction is sort of well defined, right? Okay. Okay, now the immediate question arises is that if I start with an n dimensional Euclidean space, or rather if I start with the additive group of Rn, whatever you want to talk about, because see the isomorphisms we are talking about in terms of groups, okay, but whenever we are talking about it geometrically, we are talking about them as topological spaces. So whoever is listening to this lecture, he or she should always switch between the topological notions and the group notions whenever I talk about things specifically. Yeah, so now suppose I talk about an n dimensional Euclidean space, and I talk about a lattice which is m dimensional, with the dimension of the lattice being less than the dimension of the Euclidean space. At that point, it is quite obvious that we won't get the full lattice. We won't get the full n dimensional torus, but we'll get a section of the n dimensional torus. Okay, so how does that typically follow? And to do that, we first talk about an example. So let us first write the theorem, which is I am writing the theorem first because it is quite intuitive to talk about this. Otherwise, we often first deal with examples, take observations from these examples, and then state a theorem. But in this case, I can first write the theorem because this is quite it's very obvious to think about this case whenever the lattice considered is of lesser dimension than the Euclidean space. The theorem is that sorry, so let me just fix this board one. Okay, so theorem, let L be a m dimensional lattice, let M be a m dimensional lattice in Rn, then Rn mod L. So this is isomorphic. So I am leaving this part now. First we will counter an example, and then we will see what this section should be. So example, consider R2 and L1 that is isomorphic to Z, or the one dimensional lattice, the 1D lattice. Okay, now see, this is a very fine observation to talk about. Let me change the color once, it will be better. Okay, let me take this color. See, suppose this is your let's say this is your R2, sorry, let's say this is your R. Okay, this is your R, and I want to see that how this Z is typically inside R. Now we know that Z just constitutes simply points over this Euclidean over the one dimensional surface R, but rather we are not considering it in this way, we are considering R as a helix. So we are simply considering R in this way. So So yeah, okay, so it will do it like this. Yeah, so we are considering a helix in this way, rather, one sec. Yeah, this will do. Okay, so we are considering a helix in this way, and each of these points are identified to be the integers. Okay, so suppose this is 0, this is -1, this is 1, and so on and so forth. Clear? Or if I just write down, so I get this as a helix, I get this, and I consider that each of these each of these turns, these talk about the integers. Okay, these are just the integers. Okay, and it continues, obviously it continues in this case and it continues here as well. So now what I do is that I sort of think as R2 to be the to be an infinite sheet of some elastic membrane. Okay, so I consider R2 to be an elastic sheet of some of a stretched membrane, an elastic sheet of a stretched membrane, and assuming that I actually want to, so see, if you have studied algebraic topology, I'm getting back to it once more. We know that whenever we talk about quotient topological spaces, we try to identify things together. That is, whenever we talk, say for example, whenever we talk about the torus constructed constructed topologically using a square, what we typically try to do is that we want to identify the edges, that is, we want to glue down the edges to construct the torus, as we just see. Okay, so in this case as well, to construct out this example, what we need to do is that we need to form the quotient group R2 mod Z, right? That is exactly what is the thing we want to do. And since we also need to attach a topological notion to it, so I can think of it as a topological space. I can think of R2 as a topological space, and then I can think of, thinking of R2 as a topological space, I can think of identifying or gluing together, bringing together all integer points to a single point. That is exactly the thing which we want to do. Clear? Okay. So now let's see how we can essentially do that out. Okay, one second. Yeah. Clear? So as I said that, think of R2 as a stretched infinite elastic sheet. Okay, and consider the helix we considered, and these are the integer points. What we do is, typically, if this is my R2, if this is my R2, which is a stretched infinitely long sheet, I keep turning it, I keep curling the sheet, so that, so what I do is that I keep curling the sheet, such that every full curl, that whenever we complete a full curl, the point where the full curl ends, the point where the full curl ends is identified as the integers. Okay, so what we are typically doing is that we are taking the infinite sheet and we are following the path of the helix. Okay, we are just following the path of the helix, so we are just keep curling the sheet, following the path of the helix, and whenever we complete a full curl, the point where we reach is exactly the point where the integers are placed along the helix. Therefore, every full curl will end at the exactly same point, and all the integers will fall under the exact same point, and hence we have successfully brought down every integer to a single point, because every full turn will end at the same point, every ideal full turn will end at the same point, and that exact point is being identified to be the point which represents the integers, right? So if I do the same thing, so what will I eventually get? So I will eventually get the sheet in this way, right? So I will eventually get the sheet in this way. Yeah, so it will be some sort of like this, right? So yeah, it will follow up here. I will have this here. So this is just a rolled down carpet. If you observe it, this is just a rolled down carpet. Okay, but then if you carefully observe that this is nothing but it seems to be, at least in this case, it seems to be, you know, the, or if I write it like this, so it seems to be a cylinder. It seems to be a cylinder. And how does a cylinder basically can be constructed is that, so it's basically an infinite cylinder. So how can we typically construct a cylinder out? If you observe that if I start with S, and I just scale S by R, if I just scale S by R, wait, if I just scale S by R, are you getting my point? If I just scale S by R, this just forms R, then I will eventually get a cylinder. So this is nothing but S cross R. So you can typically follow that this is nothing but S cross R, and S is nothing but T. So this is just T cross R, and this is just T1, and this is just R1, right? So what we typically conclude out from this example is that R2 mod L1 is isomorphic to T1 cross R1. In other words, the thing to observe is, here is the case T1, that is T exactly, this torus exactly corresponds to the dimension of the lattice we started with, okay, and hence it is time to fill up the theorem. So where did I write the theorem? So Rn cross L will be isomorphic to, so L is a m dimensional lattice, so corresponding to it we will get a m dimensional torus, and the rest of the Euclidean space will be just be filled by the n minus m dimensional Euclidean space. Clear? And the proof of this is very simple. There is nothing difficult to talk about the proof of this, because the proof of the theorem, okay, what we do is that we simply take V, let V be the subspace spanned by L, okay, and consider W such that W fills the rest of the portion. So I have Rn to be simply V direct product W. If you carefully observe that V will correspond to the m dimensional part and W will correspond to the n minus m dimensional part. Now if I quotient out V using L from the previous theorem, so above we have an n dimensional Euclidean space and below I have an n dimensional, above I have a m dimensional Euclidean space, m dimensional space, and in the bottom I have a m dimensional lattice, right. So I will get just a m dimensional torus, right. And in case of W, so as the way we have considered W is just isomorphic to Rn minus m, and it is completely lying outside V, because we are talking about a direct product. It is completely lying outside V in terms of in terms of its topology. Therefore, if I quotient out Rn with L, what I get is that I will need to quotient out V with L, which will give me Tm, and W completely lies outside, so it is separate from the quotiented case. So it will just give me, or rather it is better to use the term cross, it will give me, or you can also consider direct product as well, it will just give me Rn minus m. Clear? So the thing which you can often observe whenever we talk about topological notions, difficulty lies in understanding the example. The proofs are always quite easy to observe. The proofs are not always complicated. Most often it is not complicated. The complication lies while studying the examples. In fact, most of the complications lies in the 2-dimensional and the 3-dimensional Euclidean spaces. Whenever if you have studied advanced topological courses, advanced algebraic or differential topological courses, you will get to know the concepts of intersection theory. Okay. When you study intersection theory has a wide variety of applications. It has a wide variety of application in terms of probability theory, stochastic processes, dynamical systems, and in terms of topology as well. You will see that using intersection theory, it's very easy to generalize notions of the 2-dimensional or the 3-dimensional topological spaces to n-dimensional topological spaces. But the initial proof, which was confined to the 2-dimensional or the 3-dimensional topological spaces, are quite complicated. For example, there is a very famous theorem called the Jordan curve theorem, which says that suppose we are in the complex plane or we are in the 2-dimensional Euclidean plane. Or the Jordan curve theorem says that whenever we consider a simple closed curve, a simple closed contour, or a simple closed curve, this will separate the whole plane into two distinct portions, two complementary portions. One is the inside of the curve and one is the outside of the curve. The theorem seems to be quite intuitive, but the proof of it in case of the 2-dimensional plane is very complicated. Okay. But in an n-dimensional case, it's quite easy to follow from the Jordan from the intersection theory. Okay. Whatever, that's enough of discussion in this lecture. In the next lecture, we will talk about the concept of volume. Because this will be required for the main goal of this series, to talk about the Minkowski's theorem, which will eventually lead us to study the 2-square and the 4-square theorem, which are very important notions of number theory. Okay. So meet you guys in the next lecture.